Okay, so we are going to talk about figure C-4. So this is part C of experiment 7. And in the schematic, we have a 7414 inverter. So this is a Schmidt trigger based inverter, a 14 pin IC. We only are using one inverter from that chip. We have 6 of them inside that chip. Then we have a 74393 IC, which is a 4-bit counter, like I mentioned. And we are going to use that counter to control 4 light emitting diodes, D1, D2, D3, D4, which have been connected to ground using resistors R1, R2, R3, R4. Those resistors are essentially there to protect the LEDs. Because if we have a certain voltage on QA and all that voltage goes across D1, it may damage the LEDs if it is too high. So we just protect that by having a resistor in series with those LEDs so that the voltage, whatever voltage you have at pin 3, 4, 5, and 6, gets split up based on voltage division between the LED and the resistor. So the LED gets whatever it needs to turn on, and then the rest of that will go across the resistors R1, R2, R3, R4, which will essentially limit the current to the LEDs, and they hence protect the LEDs as well. So that's what we have in this diagram, and we are going to start talking about this. Um, so if you guys can make the view of the proto board your bigger view, that will help. So on all the way on the left, I have the 7414 IC. Next to that, I have the 14 pin 74393 chip, which is the 4-bit counter. I have connected the outputs of the counter, which are pin 3, 4, 5, and 6, to the positive or the long leads of 4 red LEDs on the other side. And uh, most people get that right. So they connect the positive leads or the long leads of the LEDs to pin 3, 4, 5, and 6. That's fine. But I've seen this as a common mistake that some of the students, on the negative side of the LEDs, they also need to be 4 different lines. So they all need to be separate. So I need 4 different sort of rows for the positive lines, in which I have pin 3, 4, 5, 6. I also need 4 different lines for the negative edge, or the cathode, or the negative side of the LEDs. And those sides are actually being connected to ground using those 4 resistors. So that's how I have set it up. I've given pin number 14 on both these chips to plus 5 volts. So I'm going to connect the plus 5 volts to this red wire, but I have used another wire to jump the voltage to the pin number 14 here. I have connected pin number 7 to ground here, and pin number 7 to ground here. And the 393 chip, I have connected pin number 2 of this chip to ground as well. And I did that so that if you look at the schematic, pin number 2, which is clear, is connected to ground. It is slightly different from the active low clear, and the reason is, earlier in the JK flip-flop we have active low clear, which means if you wanted to clear, you connected it to low. If you didn't want to clear, you connected it to high. Over here we have an active high clear, which means if I want to clear, I make it a 1, and if I want to not clear, then I make it a 0. So as it is counting, I don't want my outputs QA, QB, QC, QD to be all zeros, so I'm going to connect pin number 2 to 0. Maybe initially I connect that to high and then switch it back to 0. So there's a question on the chat over here. Why can't we combine the negative side of the LEDs? Well, if you see this, the negative side of the LEDs and the positive side of the LEDs is indicated by the triangle and the flat side of the LEDs on the schematic. And as you can see, all the long leads or the positive sides or the anodes of LEDs are connected to pin 3, 4, 5, and 6 of the counter. However, the negative side is connected to a different component. It is connected to resistor R1, R2, R3, R4. So if we have overlap, then we are going to essentially connect the negative to pin 3, which we do not want here. So each positive and negative needs to be on its own particular row in the proto board. The positive ones should be connected to 3, 4, 5, 6. The negative ones should only be connected to the four resistors R1, R2, R3, R4. So I hope that answers your question. Moving on. Um, so I've set up the circuit. Let's see if and this is slightly different from how I usually set up things. I like the top rail to be plus 5 volts and the bottom rail to be ground in most cases. But over here, I've made both the bottom rail and the top rail to be ground, just so that I can have a prettier um, circuit board. um, I'm using plus 5 volts only at two places, so I don't need an entire rail for that. So let's go ahead and connect plus 5 to plus 5 from analog discovery and ground to ground. And as you notice, this black wire over there is essentially connecting the top rail and the bottom rail together. So everything on the two sides is ground right now. So let's see if we can start counting with the LEDs. And I expect them to count in binary. So if they start the counting position at any arbitrary position, say for example, they start the counter at 10, which is 1010, they will start counting there. So it will go from 1010 all the way to 1111, and it will cycle around to go to 0000, and then it will keep going between 0000 all the way to 1111 based on the binary uh, count levels. So let's see. My red wire is right now on, so that's okay. My ground is connected, so that's fine. I need what do I need at my pin number 1 of the inverter? I need input from AWG. So I'm going to take a yellow wire, which is my wave generator 1, and I'm going to connect it to pin number 1 of the 7414 IC, which is the IC on the left. So I've connected yellow wire that is coming from the wave generator. So I'm going to start the wave gen. I have it as a sinusoid. I don't need that to be a sinusoid. I need this to be a square wave. So if I go down here, where is the square wave? Let's see. Um, I'm just going to look at the frequency and the amplitudes that I need to set for this. So it looks like uh, 0 to 4. Okay, so I have 0 to 4 at a frequency of 20 hertz. So 20 hertz is the frequency that I should set it up, and 0 to 4 is the amplitude. So let's say I have 20 over here, not 20k, just 20. And I'm going to set it up as a square wave. It is showing me that it goes from -1 to 1. I need it from 0 to 4. I'm going to set the amplitude to 2. So I have peak to peak as 4, and then I'm going to use my offset of 2 volts. so that it now goes from 0 to 4 volts. So that's good. 0 to 4 volts by setting amplitude as 2 and offset as 2, and the frequency I've set it up as 20 hertz, and I can start running it. And hopefully as soon as I start this, you should see the LEDs start counting 0000 all the way to 1111, and then they cycle through. So okay, so that's essentially what that is doing, but it is happening at a very fast speed because you have set it up as a 20 hertz uh, input. So what I can do is, in order to analyze this a little bit better, I can slow down the input to 1 hertz. So if you now observe the 4 LEDs, they are uh, counting in binary. So for example, if I look at uh, which one is changing the fastest, so you see the right or the topmost LED is changing the fastest because it toggles at every instant, so it keeps blinking. So that's the least significant, or Q0, and all the way to the bottom here we have Q3, and the least significant or the topmost LED is blinking 010101. The next one is going 00110011, and then 4 zeros, 4 ones, 8 zeros, 8 ones, and so on. So it's doing the count: 1111, all zeros, 1, 2, 3, 4, 5, and so on. So it goes from a count of 0 to 15, which is 16 possibilities, but in decimal it goes from 0 to 15 and cycles through. So that's essentially what the idea is with the 4-bit counter. So let's try to observe a few things here, because like I mentioned, we have set it up as a positive edge triggered counter. The input to the counter chip 74393 was a negative edge, but because we used an additional inverter in the front, it is going to behave with respect to the wave gen, it is going to behave as a positive edge triggered 4-bit counter. And to observe that, we are going to set up some oscilloscope channels. So let's see. If I scroll down, the instructions on experiment 7 say that uh, set up channel 1 to be clock and set up channel 2 to be QA, QB, QC, QD. So let's see. And I want to look at 50 clock cycles. I'm going to have to do that by using my scope channel 1 and scope channel 2 and so on. So let's see. I have an orange wire over here, which I'm going to use to look at the clock. Um, so I'm going to essentially look at the clock. I could look at the clock. Uh, well, I can look at the input itself as the clock. So I'm going to connect that to the first pin or the wavegen itself. I'm going to connect my ground to orange stripe. So channel 1 negative connected to ground. Then I have, say, blue on channel 2. And let us start with the first one, Q2. Channel 2 is connected to QA. QA is pin number 3 of the counter. So that's pin number 3 right there. And I still need to connect blue stripe to ground. So I've got that going. Alright, so I've completed the connection here, and now I can start scope, oscilloscope in waveforms. So scope is started there, and in fact I can make this slightly bigger And let's go back to the 20 hertz, because to look at 50 cycles, I need a bit of a higher frequency. So I'm going to go back to 20 hertz, then go to scope, and the time base right now is in milliseconds. That is probably too small. So I am going to go to about 200 milliseconds per division, and we'll see if that works as a start. Channel 1 is set up, channel 2 is set up. Um, so 0 to 4 volts, that is probably not going to be okay. So 1 volt per division, 1 volt per division, that gives me enough. So let's run it now. So, and turn off noise on both channel 1 and channel 2, just so that we are looking at the signal here. And also, let us make the plot width a little bit better so that we can look at things in a little bit more detail. And to begin our discussion, I will try to zoom in to show you how the count is happening. So if you see this, I'm just going to bring the trigger over here so that it stabilizes. Right, and let's make it 20 and stop for now. Okay, so the orange is the clock, and when the clock goes from low to high, I can see the output QA, which in our case is Q0, the least significant, goes from low to high and high to low and so on. So it only changes when the clock goes from low to high or the positive edge, because we used an inverter in front of a negative edge triggered counter. By using those two, we have essentially made things into a positive edge triggered 4-bit counter. And that is repeating like that. QA, that's the least significant. So it is essentially half the frequency of the clock itself. So if the clock is set to 20 hertz, the frequency of QA is 10 hertz. And I think you guys can guess what the frequencies of QB, QC, QD are going to be. They're simply going to be 5, 2.5, 1.25. So that it keeps getting divided by 2 as you move ahead in terms of the significance of the output. So let's try to look at 50 time periods. So 50 time periods would be think that it's going to be okay to look at 50 time period. So if you're able to look at that, that's channel 1 versus QA. And just to show you guys, if I move this to QB, QC, QD, which means pin 4, 5, and 6 of the counter, I'm essentially going to be looking at a slower by a factor of 2 square wave signal on the blue. I will keep the yellow or the orange, the clock signal, to be the same, and I will move this up 1, and I've got QB, and as you can see, it has slowed down a bit, exactly precisely the factor of 2. Move 1 over, that is QC, again responding to positive edge of the clock but half the frequency. And then finally the last one, which is QD, for the division of 2. So those are your 4 outputs from the 4-bit counter. Let's come back to A here. Let's just put it over there. Okay, so that finishes the discussion on the 4-bit counter. This is figure C-4, and I'm going to be using this particular board even to do part D of experiment 7. In fact, I will keep this safe even for project 3. So um, I'm going to keep this protoboard by the side and just use the same circuit, part D of experiment 7 as well as in project 3. So I'll use other protoboards. Okay, so let's see, stop the recording and take questions is what we are going to do.